So in the last video, we had seen this notion of viscous democracy, and in this video, we'll be covering more details on the same. So let's try to have some parallel between liquid democracy and social networks. The idea is that liquid democracy delegation graphs, the delegation graphs obtained in liquid democracy, and social networks, the relationship graphs in existing social networks, can be similar. And they are not identical. They're definitely not identical, but they can be similar. And think about it. You're more likely to delegate your votes to someone in your social network, so in your social circle, like someone you trust. And so modeling the similarities can be useful because you can directly use some properties of social networks that have been extensively studied for decades. So we have several properties like small world phenomenon, the rich get richer phenomenon, and strength of weak ties, etc. And there have been several algorithms as well, like for social networks. So it can be useful to kind of like build liquid democracy systems on top of existing e-networks or social networks, so as to take advantage of this. So in some ways, like currently the social networks, like they carry information, and uh, if you can build liquid democracy systems on top of that, like you kind of like enable it to carry trust or power as well. And so that is the idea. And we've seen why we may need to move to a slightly modified form of the basic model of liquid democracy, uh, because the number of connections in e-networks is typically larger than what you'd find in friendship networks, and there are many more weak ties involved. Weak ties can be acquaintances, basically. They can be acquaintances or colleagues who may not be close to you, and thus the trust factor may actually be lower on average in such networks, and thus it seems appropriate to introduce some kind of reluctance in the delegation process. And we had seen this. Trust can indeed diminish with distance. And so how exactly do we do that? So in the new setting we have here, we have a parameter alpha, which is called the damping or delegation factor. It's a value between 0 and 1, and it is kept constant throughout the delegation network. And so while calculating the score of a node, we combine alpha with the length of the delegation path as well. So it would become clear. This equation would become clear when you try to understand it with the help of the diagram on the right. So basically, we have, let's say we're trying to calculate the score of D, and we have the delegation path A to D, B to D, and C to D. These are basically the delegation paths ending at node I and ending at node D here. And we combine alpha to the power the length of the delegation path minus 1. So basically, 3 minus 1, 2 minus 1, and so on. So basically, I'm assuming each voter is basically transmitting one vote to D. And when we include this alpha to the power mod P minus 1, we're kind of like introducing some reluctance as the distance between the voters increases. So, and finally, you just take the summation. So, that is what this equation is kind of trying to represent. So, if you just try to think of trust as different fluids running from A to D, B to D, and C to D, you just kind of like modify that according to the distance, and then you take the summation. And that is exactly what is represented by this equation on the left. So let's start with case one, where alpha is kept as 0.25. And what this means is that while calculating the score of this node, so we have a vote from this node. So basically, that will be 1. And again, like a score of 1 will be added from the node on this side. And every node at a distance of 2 is going to contribute 0.25 times 1. So basically, since it's at a distance of 2, it's going to be alpha to the power mod p minus 1. So that is just going to be alpha times this. So we have 4 nodes, and it's going to be 4 into 0.25, which is 1. And so 1 plus 1 plus 1 from this node, and then it already had a vote of 1. So basically, it's going to be 4. And similarly, if I have to count for this, every node is at a distance of 1 itself. So 3 votes are going to be directly added, and it already had a vote of 1, so that's going to be 4. And I hope you're getting a glimpse of how this is working. Similarly, when alpha is set to 0.1, if you have to calculate the score of this node, so basically we first calculate the delegated votes, the scores at a distance of 1. So this is transmitting 1 vote to this, and this is transmitting 1 vote to this. It already had 1 vote in the beginning, so it's basically 3. And we have 4 nodes at a distance of uh, 2. So basically, I multiply alpha times 1 for each of these nodes. So it's going to be 4 into alpha, which is going to be 0.4. And so we had 3, and each of this is kind of contributing 0.1 to this, and they're all at a distance of 2. So the net score is going to be 3.4 for this particular node. And and similarly, if a node is at a distance of 3, we multiply alpha square times the vote that is transmitted by that node. So basically, that is how the score is calculated in the modified setting. And try to think what happens when alpha is set to 1. When alpha is set to 1, that means there's a lot of trust in our network. And this is going to work exactly the same as what we had seen before. So basically, we have 7 votes being transmitted from nodes in the graph to this particular node. So this is one. This is one. The node, assume there's a self loop here. So basically, each node also had a vote of 1 by itself in the beginning. So basically 3, then 4, 5, 6, and 7. So that is how the score of this is 7, and when alpha is set to 1. And that means it's just working exactly the same way as before, what we have seen. That is like the basic model of liquid democracy. And when alpha approaches to 0, when alpha is very small, let's try to understand how the scores would reflect in that case. Here, for the sake of simplicity, let me just ignore that 1 vote we had at the beginning for nodes x and y. So to just make the calculation simpler. So each of these k nodes is going to transmit 1 vote each, and it's going to be k here. The score of node x is going to be k, and because alpha is small, these nodes, these k nodes, the delegation transmitted by these k nodes would kind of diminish when it reaches y, and so we basically just have 1 plus node x. We just have 1 plus 1 vote from node x, and we have alpha times k, and this alpha times k is going to be a very insignificant value, so we can kind of ignore that. And so where we're getting at, when alpha approaches to 0, that means each node x can only influence the victory of its immediate neighbor. And that is what I mean by here. These k nodes kind of had no influence on node y because they were at a distance greater than 1. So that is kind of interesting. I just wanted to see various cases to just make the understanding of this model clearer. And as the alpha value is high, that means there's a lot of trust in the network, and the viscosity of the fluid in the network is basically low. And as the value of alpha is low, that means the trust is less in the network, and the viscosity of the fluid in the network is high. So just trying to visualize or make an analogy to fluids can be helpful when you're just trying to visualize how trust is transmitted in viscous democracy. So here are the references: Viscous Democracy for Social Networks and Voting in Social Networks. So basically, you can check out these 2 papers to understand about this model, the model of viscous democracy, in a lot more detail. And do subscribe for more such content. Thank you for watching.